Hi, this is Julia and Maddie, and we're here to teach you about projectile or 2D motion. Suppose a kid throws a ball. Make a prediction of what the path of the ball will look like. Did your prediction look anything like this? So why is it a curve?
Vertically, the force of gravity is always acting perpendicular to the motion of the projectile. Even though the ball is traveling upwards, it is accelerating downwards. Because this is gravity, we have a known value for the acceleration. This is called the acceleration due to gravity and has a value of 9.8 meters per second squared. Horizontally, no net force exists because the forces are balanced. What do balanced forces mean? Balanced forces mean a constant velocity and no horizontal acceleration. This is a free body force diagram for the overall motion of the ball. As you can see, only the force of gravity is noted because there are no upward or sideways forces acting on the ball. The mathematical models are delta y equals the initial velocity times time plus 1/2 the acceleration due to gravity times time squared. And delta x equals horizontal velocity times time.
Let's talk about the Earth. Imagine a satellite traveling around the world. What keeps the path circular? There is a constant pull towards the Earth and a constant acceleration due to the Earth's gravitational force pointing inwards to the core of the Earth, while meanwhile, the speed is tangential to the circular path and is constant. Now, Maddie is going to show you what the acceleration and the speed looks like. The black pen is the velocity that the satellite is experiencing. As you can see, it is following the circular path of the Earth. Maddie is drawing the acceleration due to the gravitational force of the Earth. This points to the center of the Earth and is equal at each step of the path. Now, Maddie is drawing the speed. The speed is tangential to the course. It is also congruent at each step of the path. But remember, the velocity changes because the satellite is constantly changing direction. It is the same magnitude, but not the same sign.
Remember that force pulling inwards? Well, that's known as centripetal force. To calculate it, you only need the velocity and the radius. The model is AC equals v squared over r, where v is the velocity and r is the radius.
Let's work on some example problems. So say we had a table that was 3 meters tall and we had a ball, but that ball has an initial velocity of 0. And all of a sudden, it starts rolling off the table and ends right up there. Its velocity is 7 meters per second as it's rolling. So let's go back to the kinematic model. Delta y equals the initial vertical velocity times time plus 1/2 the acceleration due to gravity times time squared. We know that our height is 3 meters, and therefore our delta y, or our change in the vertical distance, is 3 meters. We know that the standard number for acceleration due to gravity is 9.8 meters per second squared. And like I said earlier, our initial velocity is 0 meters per second. So, at what time will it land? Well, we know that our delta y is 3 meters, so we put that in our equation, and because our initial velocity is 0, that will wipe out in the next part. Therefore, we're left with 1/2 a sub g times time, and therefore 3 meters equals 1/2 times our known value for the gravitational acceleration, which is 9.8 meters per second squared, times time squared. This should be squared, my fault. And therefore, we divide by 1/2 9.8 meters per second squared. We divide 3 by that, and we're left with 0.6122 seconds squared equals time squared. And then we take the square root of both sides, and we're left with time equals 0.782 seconds. And therefore, it will land at 0.682 seconds.
So let's do a motion map. As you can see, all the purple lines are the same length. This is because the ball is moving with a constant horizontal velocity. The pink lines, however, are different lengths because the vertical velocity changes due to the acceleration of gravity.
The pink lines are progressively getting longer, as you can tell. So now that we know how to solve projectile motion and the ins and outs of the centripetal force, let's discuss some real-life application. Like, for example, the death spiral, which uses 2 figure skaters, a male and a female, and the male and the female hold on with their hands, and the female's head almost hits the ice, but instead she travels in a circular path. Centripetal forces working in this. Or my personal favorite, because I am a pole vaulter and belong to the field team of my track and field team, is the hammer throw. And it's especially going to be popular because the Olympics are coming up. In the hammer throw, the centripetal force is acting as the hammer thrower revolves the ball around in a circular path. And when he lets go of the hammer travels in a projectile motion.